The primary idea behind the Aesc is to have both an affordable and portable device that can continuously track the path of the sun. This is done to effectively supply enough power to keep devices running from a reservoir of stored energy, of which is collected by the panel. The most important concept of a solar tracker is to be classed as an efficient solar cell of self-sufficiency. The Aesc provides a realistic solution for the need of readily available power for situations where power isn't as easily or readily accessible.
The process of making our solar panel begins with our titanium layer. We first heat it to remove any impurities, such as oxygen, or any other components that might have been airborne. This is also meant to prime the surface for the dye staining process. The next step of our process consists of staining the titanium layer with a ruthenizer chenodeoxycholic acid substance. This embeds an absorbent layer for the photons to travel in. This substance is meant to have the layer sit for roughly 36 to 48 hours, but with the assistance of the acid, we can reduce this to 12 to 14 hours. The next step of the process is to heat the conductive platinum layer. This is also meant to remove any impurities such as oxygen and should only sit for about 10 minutes as the layer is very thin. This is also meant to prime the surface for the gasket adhesive. The next step of the process is the redox recombination step. This is done after combining the portions of the conductive faces together. We add iodide into pre-drilled holes. This helps by re-adding missing valence electrons with an oxygenated layer.
Here we have our PCB design. We are using two PIC-18s, one for controlling our reference sensor and one for controlling our panel. The system starts with the left PIC, where it reads the accelerometer to get a general idea of where to start looking. Then with the two servo motors and a UV sensor, it finds the sun. Once it's inside its predefined threshold, the left PIC-18 activates the right PIC-18. The right PIC-18 then uses the easy driver to control a 12-volt stepper motor to turn the panel and a 5-volt stepper motor to tilt the panel. It then compares the panel UV sensor to the reference UV sensor, and when it's within the threshold, the right PIC-18 deactivates.
Our panel will continually feed the battery with 12 volts and 500 milliamps of current. Our battery outputs the 5 volts needed for our microcontrollers and their respective components. When the microcontrollers deem necessary to turn the panel, our battery is also able to output 12 volts for our stronger stepper motor. We needed a stepper motor that could handle larger loads in case the solar cells we synthesized needed heavy metal frames. The panel will move in even smaller increments when in practice.